The weighing room is silent in the hour before dawn. Outside, the Pittsburgh rail yard hums faintly with distant locomotives, but inside the brick walls of the Hammond Foundry's materials warehouse, the only sound is the settling of floor timbers beneath cast iron pillars. A single gas lamp burns near the entrance, throwing long shadows across the room's centerpiece. A massive beam balance scale, its brass fittings dulled by years of coal dust, its knife-edge bearings resting in polished agate cups. William Marsh, the foundry's materials clerk, arrives at 5:15, as he has every morning since 1887. He carries a wooden case containing certified test weights, each stamped with the year of calibration and the seal of the Pennsylvania Bureau of Weights and Measures. The ritual is always the same. Before the day's shipments are weighed, before the furnace teams begin measuring out pig iron and limestone, Marsh tests the scale with a 50-pound standard weight. The procedure takes less than 3 minutes. The scale should balance perfectly, beam level, pointer centered. It always has. This morning it does not. Marsh places the test weight on the left pan. He slides the counterweight along the graduated beam until the pointer should settle at 0. But the beam sags leftward. The test weight appears heavier than 50 pounds. Not dramatically so, perhaps 3 or 4 ounces, but the deviation is unmistakable. Marsh removes the weight, inspects it for moisture or foreign material, finds nothing. He tries again. Same result. He checks the scales level. Perfect. He examines the knife edges under lamplight. Clean, sharp, undamaged. By the time the morning shift arrives at 6, Marsh has tested the scale 9 times. 9 times the test weight reads heavy. He reports the discrepancy to the shift foreman, who dismisses it as user error. But Marsh is certain. For 2 years he has performed this same test every morning without incident. The scale is lying. At 8:30, after 2 hours of normal weighing operations, Marsh tests the scale again. This time, the 50-pound weight balances perfectly. The error has vanished. He says nothing. The next morning, the weight reads heavy again. For 6 consecutive mornings, the test weight appears 3 to 4 ounces heavier than its certified mass. By mid-morning, the error disappears. The scale performs flawlessly throughout the workday, handling loads from 20 pounds to 800 pounds with consistent accuracy. Marsh begins keeping a log. He records the exact time of each test, the ambient temperature, the weather conditions, the position of weights being measured. The pattern is absolute. Only after the scale has remained still overnight does the test weight read heavy. Only in the first hour of operation. By the second week, other workers notice. The furnace foreman mentions that early morning shipments of pig iron seem inconsistent with afternoon measurements. A rail clerk notes discrepancies in coal weights logged before 7 versus those logged after 9. The variations are small, 0.5%, sometimes less. But in an operation moving hundreds of tons per week, 0.5% matters. Marsh begins testing the scale at different hours. A test at midnight, after the scale has been idle for 6 hours, shows no error. A test at 3 in the morning, after 9 hours of stillness, shows the weight reading heavy again. The longer the scale sits motionless, the more pronounced the error becomes. The foundry manager orders a complete inspection. The scale is disassembled piece by piece. The knife edges are measured with calipers and found to be perfectly symmetrical, sharp, and true. The beam is checked for warping or corrosion. The pans are weighed and found identical. The supporting frame is plumbed and leveled to within a 1/16 of an inch. Every component meets specification. The scale is reassembled, tested, and declared sound. The next morning, the test weight reads heavy again. Marsh suggests replacing the scale entirely. The manager approves the expense. A new beam balance, freshly calibrated by the manufacturer, arrives from Philadelphia in October 1889. New scale is installed with great care. Its knife edges are honed to surgical sharpness. Its agate bearings are hand-polished. For 3 days, it performs perfectly morning and afternoon alike. On the 4th morning, the test weight reads heavy. The pattern has returned. Workers begin to whisper about the room itself, about unseen forces, about the possibility that weight itself behaves differently in darkness. Marsh does not entertain such speculation, but he has no alternative explanation. The certainty of measurement, the foundry's operational cornerstone, has become unreliable in ways no one can explain. By November, the anomaly has cost the foundry measurable money. A shipment of iron billet, weighed early in the morning and certified at £4,820, is reweighed by the customer and found to be £4,802, a discrepancy of £18. The foundry is forced to issue a credit. Another shipment, weighed just after dawn, arrives short by similar margins. The customer threatens to find a new supplier. The foundry's reputation for precision, built over 2 decades, is eroding. Management considers whether sabotage is occurring, whether a competitor has bribed workers to manipulate weights, but surveillance reveals nothing. The scale simply behaves differently after a night of stillness. Marsh begins arriving earlier, sometimes at 4 in the morning, to document the effect. He discovers that the error is not instantaneous. If the scale is moved even slightly during the night, if someone brushes against it, or if the building settles enough to disturb the beam, the morning test shows less error. The scale must remain in perfect stillness for the anomaly to fully develop. He places chalk marks on the floor around the scale's base and instructs workers not to approach it after the evening shift ends. The next morning, the chalk is undisturbed, and the test weight reads 4 ounces heavy. He tries isolating the scale from vibrations by placing felt pads under the frame. No change. He tries covering the scale with canvas to prevent air currents from affecting it. No change. The foundry hires a consulting engineer from Carnegie Steel, a man named Horace Venn, who has designed weighing systems for blast furnaces across Pennsylvania. Venn spends a week observing the scale's behavior. He confirms Marsh's measurements. He rules out magnetic interference, uneven floor loading, and barometric pressure effects. He examines the possibility that the test weight itself is changing mass due to moisture absorption, but the weight is solid brass, impervious to humidity. Venn suggests moving the scale to a different location within the warehouse, a corner room with more stable temperature and less foot traffic. The scale is relocated in December. For 2 weeks it performs normally. Then the pattern resumes. Morning tests show the weight reading heavy. Afternoon tests show perfect accuracy. Venn returns to Pittsburgh baffled. He writes in his report, "The instrument is mechanically sound. Its behavior defies explanation under known principles of static equilibrium. I recommend the foundry maintain the scale in continuous motion to prevent the anomaly from developing." The foundry implements this advice, assigning a worker to disturb the scale every few hours throughout the night. It works, but the solution is absurd. A precision instrument should not require disturbance to maintain accuracy. A beam balance scale operates on the principle of the lever, one of the 6 classical simple machines. The scale's horizontal beam pivots on a knife-edge fulcrum, a hardened steel wedge ground to a sharp line and resting in a complementary groove, often made of agate or sapphire. When objects of equal mass are placed on pans suspended from each end of the beam remains level. When masses differ, the beam tilts toward the heavier side. By sliding a calibrated counterweight along the beam's length, the operator can determine the unknown mass by finding the position where balance is restored. The accuracy of this system depends on geometric precision. The knife edge must be perfectly straight and centered. The beam must be rigid and symmetrical. The pans must hang freely without friction. Any distortion in these relationships introduces error. A knife edge worn on one side will create a false pivot point. A bent beam will transfer weight unevenly. A sticky bearing will resist motion and create hysteresis, where the scale's reading depends on the direction from which balance is approached. For this reason, precision scales are maintained with obsessive care. Their components are kept clean, their knife edges are resharpened annually, and their bearings are inspected for wear. The knife edge bearing is the critical element. It concentrates the entire beam's weight and all applied loads onto a line of contact less than 1/1000th of an inch wide. This minimizes friction and allows the beam to rotate freely in response to tiny imbalances. But this concentration of force also creates enormous pressure, thousands of pounds per square inch, at the point of contact. The hardness of the materials involved prevents visible deformation under normal use, but at the microscopic level, elastic deformation occurs. The knife edge compresses slightly into its bearing. The bearing's surface yields fractionally. These deformations are reversible when load is removed, but they exist. Under ideal conditions, these micro-deformations are symmetrical and do not affect balance. The scale responds identically to loads on either side, but conditions are never perfectly ideal. Temperature changes cause expansion and contraction. Molecular forces between surfaces create adhesion. Microscopic roughness creates friction. Over time, even imperceptibly small asymmetries in how the knife edge settles into its bearing can alter the effective geometry of the lever. The scale begins to lie, not because its components have failed, but because the static equilibrium it was designed to maintain has subtly shifted. The question at Hammond Foundry is not whether such shifts occur, they must, but why they occur only after prolonged stillness, and why motion erases them. In January 1890, Marsh begins a new series of tests focused not on the weights, but on the scale itself. He measures the ambient temperature in the weighing room at hourly intervals. Overnight, the temperature drops by 15 to 20 degrees Fahrenheit as the building's coal-fired heating system is allowed to cool. By morning, the room is cold enough that breath condenses. By midday, after furnaces and forges have been running for hours, radiant heat has warmed the space considerably. Marsh wonders whether thermal contraction of the scale's components could alter its geometry. He performs a simple experiment. On a Saturday evening, after the warehouse has closed, he places the test weight on the scale and notes the reading. He returns Sunday morning before sunrise and finds the scale reads the weight as heavier. But this time, instead of removing the weight immediately, he waits. He watches the scale for an hour as pale winter light fills the room. Gradually, imperceptibly, the beam begins to shift. By the time the room has warmed to its daytime temperature, the scale reads correctly. The weight has not changed. The scale has adapted. He consults with Venn, who suggests examining the knife edges under magnification. Using a jeweler's loupe, they inspect the primary fulcrum knife edge where it contacts the agate bearing. The contact line is too small to see clearly, but they notice something else. Around the bearing, on the agate's polished surface, there are faint marks, patterns of wear invisible to the naked eye but evident under magnification. The marks are not symmetrical. One side of the bearing shows slightly deeper contact impressions than the other, suggesting the knife edge has settled into the bearing with a fractional tilt. Over hours of stillness, this tilt could become more pronounced as molecular forces between the surfaces increase. Venn hypothesizes that the knife edge, despite its hardness, is experiencing elastic creep, an extremely slow deformation under sustained load. When weight is applied to the scale, the knife edge presses into the bearing with enormous force concentrated on a microscopic line. Over hours, the metal yields fractionally, perhaps a few millionths of an inch. This deformation shifts the effective pivot point of the beam. If the shift is not perfectly symmetrical, one side of the scale becomes mechanically favored. The weight appears heavier because the lever's geometry has changed. When motion resumes, when the scale is used, the knife edge rolls slightly in its bearing, releasing the accumulated strain and restoring symmetry. Venn recruits two colleagues, both specialists in precision instrumentation, to investigate further. They arrive in February with sensitive measuring tools, micrometers capable of resolving 10,000ths of an inch, dial indicators, and thermal probes. They spend 3 days mapping the scale's behavior under controlled conditions. They measure the beam's deflection under load. They track the knife edge's position in its bearing using a dial indicator pressed gently against the beam's end. They record the room's temperature every 15 minutes. The data they collect reveals a pattern more complex than thermal contraction alone. When the scale is loaded and then left undisturbed overnight, the knife edge settles deeper into its bearing as the temperature drops. Thermal contraction shortens the beam by a fraction of a millimeter and tightens the contact between knife edge and agate. But the settling is not purely elastic. Over hours, Surface adhesion between the steel knife edge and the polished agate increases. Molecular forces, negligible when surfaces are in motion, become significant when surfaces remain in intimate contact for extended periods. The knife edge effectively bonds to the bearing at a microscopic level. This bonding resists rotation and increases the force required to restore equilibrium. The engineers test this hypothesis by deliberately vibrating the scale after it has sat overnight. They tap the frame gently with a mallet. Immediately, the test weight's reading drops closer to normal. The vibration has broken the adhesive bond and allowed the knife edge to reposition itself in the bearing. They test again by applying a small lateral force to the beam before weighing. Same result. Motion, even slight motion, resets the scale's geometry. They confirm that the error increases with the duration of stillness. After 4 hours of immobility, the error is minimal. After 8 hours, it is pronounced. After 12 hours, it reaches its maximum. They also discover that the error is load-dependent. The heavier the load applied to the scale after a period of stillness, the more pronounced the initial error appears. A 5-pound test weight shows negligible deviation. A 50-pound weight shows several ounces. An 800-pound load shows more than a pound. This suggests that the knife edge's deformation and adhesion are cumulative effects, worsening under greater stress. The engineers conclude that the scale is not defective. It is behaving exactly as precision mechanics dictate. The problem is that no one had previously observed or documented this behavior because most scales are in frequent use and never remain still long enough for the effects to accumulate. The phenomenon at Hammond Foundry is the result of overlapping mechanical behaviors, none of which are individually unusual, but which combine in unexpected ways when a precision instrument is left motionless for extended periods. The primary cause is elastic deformation of the knife edge bearing under static load. When the scale's beam rests on its fulcrum, the knife edge presses into the agate bearing with a force determined by the beam's own weight plus any applied loads. Over hours, the steel knife edge compresses microscopically into the agate, and the agate yields fractionally under pressure. This deformation is elastic. It recovers when load is removed, but while present, it shifts the effective geometry of the lever. The second factor is thermal contraction. As the weighing room cools overnight, the steel beam and brass fittings contract more than the cast iron frame. This differential contraction alters the spacing between components and increases the contact pressure at the knife edge bearing. The beam effectively tightens against its fulcrum. The increased pressure accelerates elastic deformation and enhances surface adhesion. By morning, the knife edge has settled into the bearing in a slightly tilted position, favoring one side of the scale over the other. This tilt is invisible and unmeasurable without specialized instruments, but it is sufficient to alter the scale's indication by several ounces. The third factor is surface adhesion and static friction. When two polished surfaces remain in contact without motion, molecular forces cause them to adhere more strongly than they would if moving. This effect, known as stiction, increases the force required to initiate motion. In a knife edge bearing, stiction resists the beam's rotation and introduces hysteresis into the scale's response. When the test weight is placed on the pan, the beam must overcome static friction before it can move to indicate the true weight. During this initial resistance, the scale's reading appears heavier than it should. Once motion begins, the adhesive bonds break, friction drops to its kinetic value, and the scale corrects itself. The fourth factor is elastic creep and microsettling. Even hardened steel exhibits time-dependent deformation under sustained stress. Over hours, the knife edge's contact line spreads fractionally as atoms in the crystal lattice shift position. Simultaneously, microscopic surface irregularities on the bearing compress and settle. These effects are reversible over long timescales but accumulate during the period of stillness. When the scale is first loaded in the morning, these accumulated deformations create a false lever geometry. Motion, any motion, disturbs the settled state and allows the components to return to their nominal configuration. Venn's final report to Hammond Foundry, submitted in March 1890, explains the phenomenon in precise engineering terms. He recommends 3 corrective measures. First, the scale should be disturbed briefly each morning before use, either by manually lifting and lowering the beam or by placing and removing a small weight several times. This resets the knife edge bearing and breaks surface adhesion. Second, the weighing room should maintain more consistent temperature throughout the night to minimize thermal contraction effects. Third, the knife edges and bearings should be inspected and replaced more frequently to prevent the accumulation of wear patterns that encourage asymmetric settling. The foundry implements these recommendations. Morning weighing errors cease, but the episode leaves a lasting impression on those who witnessed it. William Marsh continues as materials clerk for another 12 years, but he never again trusts a scale that has been sitting idle. He always tests it first, disturbs it, lets it settle, and only then proceeds with measurement. He understands now what the textbooks do not teach, that precision instruments are not passive observers of the physical world. They are active participants, subject to the same forces they measure, vulnerable to time and stillness in ways that motion obscures. A scale at rest is not a scale in equilibrium. It is a scale negotiating invisibly with gravity, temperature, and molecular forces, finding a balance that may not be true. Only motion reveals the lie. Only motion restores truth.